The 90% idle problem. Modern Ethereum nodes spend over 90% of their time waiting for the disk to retrieve data rather than actually executing code. This I/O bottleneck is the structural reason why gas fees spike during high demand, regardless of how much hardware you throw at a standard node. While Layer 2s try to offload the work, parallel EVM projects in 2026 like Monad and SayV2 are rewriting the underlying ledger architecture to process thousands of transactions simultaneously. It is not just about raw speed, it is about changing the fundamental way a computer remembers what you own. This transition relies on a mechanism called optimistic execution. The sequential execution trap. The standard Ethereum virtual machine is strictly sequential. If Alice sends a token to Bob and Charlie sends a token to Dave, the network processes them one after the other, even though the two actions have nothing to do with each other. This legacy design ensures absolute consistency, but leaves modern multi-core processors idling while a single thread does all the work. Solving this requires more than just adding more cores. It requires a way to predict which transactions will collide before they even run. This brings us to the mechanism of optimistic execution. Optimistic execution and conflict resolution. Optimistic execution assumes that most transactions in a block do not interact. Monad and SayV2 execute these transactions in parallel across multiple threads immediately. Only after execution does the system check for conflicts. If two users both try to spend the same $10, the system detects the overlap, throws out the second result, and reruns it. This trial and error approach is actually significantly faster than waiting in line because, statistically, most on-chain actions are independent events. However, even the fastest execution engine fails if the database cannot keep up with the results. The database storage breakthrough. The real innovation in 2026 is not the parallel code, but the custom state databases like MonadDB. Traditional Ethereum nodes use a storage structure called a Patricia Merkle tree, which requires multiple slow disk reads for every single balance check. Monad redesigned this as a flat database that allows for asynchronous I/O. This means the processor can start the next transaction while the disk is still fetching the data for the last one. By removing the wait time between the processor and the storage, these protocols are hitting 10,000 transactions per second without sacrificing the security of the Ethereum standard. This structural shift creates a new landscape for decentralized application design. The end of App-Chain Fragmentation. The transition to parallel execution and asynchronous storage marks the moment blockchain architecture finally moves past the limitations of the single-core era. By solving the I/O bottleneck through MonadDB and adopting the optimistic execution model seen in SayV2, we are seeing a shift in the fundamental value proposition of a Layer 1. For years, the industry assumed that high-demand applications needed their own dedicated chains to avoid congestion. This data shows that a sufficiently optimized EVM state can handle high-frequency trading and social media interactions on a single shared ledger. For developers, this means synchronous composability is back on the table. You no longer have to choose between a fast environment and one where all the liquidity lives. The trade-off has shifted from scaling through fragmentation to scaling through raw engineering efficiency. Watch for the first major decentralized exchange to migrate back from an app chain to a parallelized general-purpose network as the ultimate stress test of this theory. Subscribe for more